Section 25 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Rolt Wheeler. Geology, Chapter 13, Historical Geology, Part 2. In the Grand Canyon and Montana, determinable fossils have been found in the less changed sediments, but they are too few and scanty to indicate much of the life of the times. Evidences of life are not wanting in the metamorphic rocks of the eastern and northern regions, but they are indirect. The strata of crystallized limestone are indications of the presence of animal life in the Algonkian seas. The great quantities of graphite diffused through many of the schists and the beds of iron ore likewise tend to show the existence of plants at the same time. More conclusive are the determinable fossils obtained in the Belt series of Montana and in the Grand Canyon series, which include the tracks of worms, brachiopods, and fragments of large crustacea referable to the Eurypterida. Such remains imply a long antecedent history of life, the records of which remain to be discovered. With regard to the comparative value of the Precambrian rocks in the chronology of geological history, no precise statement can be made, but various circumstances show that they must represent an enormous period of time. From the general character of the Cambrian fauna, it must be regarded as certain that life had existed on the earth for a long series of ages before that fauna appeared, in order that such well-advanced grades of organization should then have been reached. One of the most interesting chapters of geological history would be supplied if some adequate account could be given of the stages of this long Precambrian evolution. The Paleozoic is the oldest of the three main groups into which the normal fossiliferous strata are divided, continues Scott. It forms the first legible volume of the Earth's history, and in interpreting it, speculation and hypothesis play a much less prominent part than in the Precambrian volume. The Paleozoic rocks are conglomerates, sandstones, shales, and limestones, with quite extensive areas of metamorphic rocks and associated igneous masses, both volcanic and plutonic. The thickness of these rocks is very great, estimated in Europe at a maximum of 100,000 feet. This does not imply that such a thickness is found in any one place, but that if the maximum thicknesses of each of the subordinate divisions be added together, they will amount to that sum. In this country, more than 25,000 feet of Paleozoic strata are exposed in the much folded and profoundly denuded Appalachian Mountains, but in the Mississippi Valley they attain only a fraction of that thickness. These rocks are, in the vast majority of cases, of marine origin, but some freshwater beds are known, and very extensive swamp and river deposits have preserved a record of much of the land life of the era, especially of its later portions. That there must have been land surfaces is abundantly shown by the immense thickness and extent of the strata, all of which were derived from the waste of the land. Both in Europe and in North America, the land areas were prevailingly toward the north and are doubtless indicated, in part, by the great regions of the Precambrian metamorphic rocks. The general character of the Paleozoic beds shows that they were, in large measure, laid down in shallow water in the neighborhood of land. Their great thickness indicates further the enormous denudation which the land areas underwent. The calculation has not been made for this country, but for Great Britain, Geikie states that the lower half of the Paleozoic group represents the waste of a plateau larger than Spain and 5,000 feet high, cut down to base level. Very widespread disturbances of the Earth's crust before the beginning of the Paleozoic era and at its close have produced well nigh universal unconformities with both the underlying Precambrian and the overlying Mesozoic rocks. At only a few points are the transitional series found. Early in Paleozoic time were established the main geographical outlines which dominated the growth of the North American continent, a growth which was for the most part steady and tranquil. These conditions may be briefly stated as the formation of a great interior continental sea, divided from the Atlantic and the Pacific by more or less extensive and variable land areas. There are thus three principal regions of continental development: those of the Atlantic and Pacific borders and the interior. In addition, the eastern border is subdivided by Precambrian ridges into subordinate areas of deposition. At the present time, the surface rocks over the eastern half of the continent are prevailingly Paleozoic, extending chiefly southward and southeastward from the great Precambrian mass of the north. Paleozoic time was of vast length, perhaps exceeding that of the combined Mesozoic and Cenozoic eras. The subdivisions of the Paleozoic are very clearly marked, locally often by unconformities, but on a wide scale by the changes in the character of the fossils. Paleozoic life possesses an individuality not less distinctly marked than that of the group of strata, which demarcates it very sharply from the life of succeeding periods and gives a certain unity of character to the successive assemblages of plants, floras, and of animals, faunas. The era is remarkable both for what it possesses and what it lacks. Among the plants, the vegetation is made up principally of cryptogams, seaweeds, ferns, club mosses, and horsetails. Especially characteristic are the gigantic tree-like club mosses and horsetails, which are now represented only by very small herbaceous forms. The only flowering plants known are the gymnosperms, the cyads, and their allies. No angiosperms have been discovered. Paleozoic forests must have been singularly gloomy and monotonous, lacking entirely the bright flowers and changing foliage of later periods. The Paleozoic fauna are largely made up of marine invertebrates, in the earlier periods entirely so. For example, so far as we have yet learned, though land life surely began before the oldest records of it yet discovered. Graptolites and hydroid corals, true corals, echinoderms, especially crinoids, cystidines and blastoids, long-hinged and hingeless brachiopods, mollusca, particularly of the nautiloid cephalopods, and the crustacean groups of trilobites and Eurypterida, are the most abundant and characteristic types of animal life. Insects, centipedes, and spiders are common toward the end of the era. Cambrian rocks contain no fossil vertebrates, but they make their appearance in the Ordovician. For long ages, the only vertebrates were fishes and certain low types allied to the fishes, but at the end of the Devonian and in the Carboniferous appeared the amphibia, followed in the Permian by true reptiles. Teleos, such as make up by far the largest part of the modern fish fauna, both marine and freshwater, as well as birds and mammals, are entirely absent from the Paleozoic. The overwhelming majority of Paleozoic species, and even genera, fail to pass over into the Mesozoic, and even in the larger groups, which continue to flourish almost always, a more or less complete change of structure occurs, so that Paleozoic corals, echinoderms and fishes, for example, are very markedly distinct from those which succeeded them. The difference is generally in the direction of greater primitiveness of structure in the older forms, Paleozoic types standing in somewhat the same relation to subsequent types as the embryo does to the adult. In the vast periods of time included in the Paleozoic era occurred some remarkable climatic vicissitudes. Times of widespread glaciation occurred in the Lower Cambrian of Norway and China, probably of Australia, and perhaps also of South Africa, in the Devonian of South Africa, and in the Permian of the latter region, India, Australia, and South America, perhaps also in Europe and North America. For most of the era, however, the climate appears to have been mild and equable on the whole, very much of the same kinds of animals and plants occurring in high as in low latitudes. In short, we can detect no evidence of climatic zones as being distinctly marked in those periods. So far as they are accessible to observation, the Cambrian rocks are chiefly such as are laid down in shallow water near shore, conglomerates, sandstones, and shales, which are ripple marked in a way that betrays their shoal water origin. During Cambrian times, the sea was slowly advancing over the land in North America, and the geography of the continent was very different at the close of the period from what it had been at the beginning. In the Lower Cambrian, the land areas are inferred to have been somewhat as follows. First, there was the great northern mass of crystalline Archean and Algonquian rocks, but this was probably much more extensive than the present exposures of Precambrian rocks would indicate. It probably covered the whole Mississippi Valley down to 30° north latitude and extended westward beyond the Rocky Mountains. Long narrow strips of land, alternating with narrow sounds, occupied part of New England and the maritime provinces of Canada, while an Appalachian land, whose western line is marked by the present Blue Ridge, extended eastward an unknown distance into the Atlantic. On the western shore of the Appalachian land was a narrow arm of the sea, which opened south and nearly separated this land area from the great mass of the continent. The site of the Sierra Nevada was occupied by a long narrow land, running from Puget Sound to Mexico, and another such area was found in eastern British Columbia. The Great Basin region was under water. Around these shores were laid down the coarser deposits of the Lower Cambrian, with great masses of shales and thick limestones in deeper water. Much interest necessarily attaches to Cambrian fossils, for excepting the few and obscure organic remains obtained from Precambrian strata, they are the oldest assemblage of organisms yet known. They form no doubt only a meager representation of the fauna of which they were once a living part. One of the first reflections which they suggest is that they present far too varied and highly organized a suite of organisms to allow us for a moment to suppose that they indicate the first fauna of our Earth's surface. Unquestionably, they must have had a long series of ancestors, though of these still earlier forms such slight traces have yet been recovered. Thus, at the very outset of his study of stratigraphical geology, the observer is confronted with a proof of the imperfection of the geological record. When he begins the examination of the Cambrian fauna, so far as it has been preserved, he at once encounters further evidence of imperfection. Whole tribes of animals, which almost certainly were represented in Cambrian seas, have entirely disappeared, while those of which remains have been preserved belong to different and widely separated divisions of invertebrate life. Of the plants of the Cambrian strata, nothing is surely known. Certain marks on the bedding planes of strata have been regarded as seaweeds, but they are too obscure for determination, and many are worm tracks. The fauna is principally made up of trilobites and brachiopods, but many other types are represented also. Trilobites have a more or less distinctly three-lobed body, at one end of which is the head shield, usually with a pair of fixed compound eyes. At the other end is the tail shield, and between the two shields is a ringed or jointed body made up of a variable number of movable segments. The trilobites display an extraordinary variety in form and size, in the proportions of the head and tail shields, in the number of free segments, and in the development of spines. Brachiopods are among the most abundant of Cambrian fossils. Most of them belong to the lower order of the class Inarticulata, in which the shells are mostly horny and the two valves are not articulated together by a hinge. The horny-shelled types, Linarsonia, Lingulepsis, and Lingulella, are of great interest, as they differ but little from certain brachiopods which still exist. The second order of brachiopods, the Articulata, which have calcareous shells connected by an elaborate hinge, were more common in the Upper Cambrian. Sir Roderick Murchison divided his great Silurian system primarily into two parts, Upper and Lower. This method of classification is generally followed even at the present day, although it is widely recognized that the most decided break in the entire Paleozoic group is the one between these divisions. In 1879, Professor Lapworth proposed to give due emphasis to this distinction by erecting the Lower Silurian into a separate system, the Ordovician. The name is taken from the Ordovici, the ancient British tribe which dwelt in Wales during Roman times. Lapworth's example is now largely followed in England and the United States, but on the continent of Europe the name Silurian is still retained for both systems. The passage from Cambrian to Ordovician was gradual, without any marked physical break. Only where the Upper Cambrian is sandy, as in New York, is a decided change in the character of sedimentation. In the latter part of the Cambrian, a large inland sea had been established over what is now the Mississippi Valley, and, with frequent fluctuations in depth and modifications in form, it was to persist for long periods as one of the salient features of Paleozoic geography. This sea was separated from the Atlantic by the landmass called Appalachia, and on the western side it was demarcated from the Pacific by islands of undetermined size. At the end of the period came a time of widespread disturbance, upheaval, and mountain making, the traces of which are still plain in North America and Europe, especially along the Atlantic slope of each continent. The interior sea appears to have been entirely drained. At all events, no deposits transitional to the Silurian are known from that region. In the west and northwest, large areas remained land for long periods, but the interior sea was soon re-established in the Mississippi Valley. Some narrow strips of land were added to the margin of the Cambrian coasts, and on a line running through southern Ohio, Kentucky, and Tennessee, a low, broad arch, the formation of which appears to have begun early in the Ordovician, was forced up by lateral compression. This is called the Cincinnati anticline or axis. Ordovician life displays a notable advance over the Cambrian, becoming not only very much more varied and luxuriant, but also of a distinctly higher grade. During the long ages of the period also, very decided progress was made, and when the Ordovician came to its close all the great types of marine invertebrates and most of their important subdivisions had come into existence. In a general way, the life of the Ordovician is an expansion of that of the Cambrian, though but little direct connection between the two can yet be traced, and evidently there were great migrations of marine animals from some region which cannot yet be identified. Several groups of invertebrates attained their culmination and began to decline in the Ordovician, becoming much less important in subsequent periods. Thus the graptolites, the cystoidean order of echinoderms, the straight-shelled cephalopods, orthoceratites among mollusks, and the trilobites were never so abundant and so varied as during this period. In America, no plants above the grade of seaweeds and coralline algae have been discovered, but in Europe a few of the higher cryptogams are doubtfully reported. The flora of the Devonian, however, renders it highly probable that land plants were already well advanced in the Ordovician, and their remains may be discovered at any time. This must remain a matter of accident, for the known Ordovician rocks are almost all marine, which is not a favorable circumstance for the preservation of land plants. Such discoveries have indeed already been reported, but the evidence for them is not satisfactory. The general disturbance which closed the Ordovician period appears to have greatly increased the extent of the continent. An important feature in the Silurian geography of eastern North America was the establishment of the Cumberland Basin, or Appalachian Mediterranean, as it has been called. This large sea lay at the eastward of the interior sea, from which it would seem to have been either completely separated, or so nearly so that the species of marine animals inhabiting the two bodies of water were very different. The Cumberland Basin was east of the Catskill-Helderberg line in New York, and its western shore crossed New Jersey and curved westward beyond the center of Pennsylvania, where it ran southwest more or less parallel with the Appalachian line, toward which it curved eastward in southern West Virginia. The interior sea underwent a succession of oscillations much like those which had affected it during the Ordovician. It was apparently closed at the south, but extended northwestward to the Arctic Sea, while its east-west diameter had been greatly reduced from that of the Ordovician. Silurian life is the continuation and advance of the same organic system as flourished in the Ordovician, certain groups diminishing, others expanding, and some new groups now make their first appearance. In parts of North America, the Silurian passed so gradually and gently into the Devonian that it is difficult to draw the line between the two systems. Some disturbances, however, took place in Ireland, Wales, and the north of England, for in these localities the Devonian lies unconformably upon the Silurian. In other parts of Europe the transition is gradual. Comparing the rocks of the Ordovician, Silurian, and Devonian, as these are developed in the Appalachian and adjoining regions, a certain rhythmic or periodic recurrence of events may be discovered among them. Each system is characterized by a great and very widespread limestone formation, and in each the limestone is succeeded by shales or other clastic rocks, due to an increase of terragenous material, and each was closed by a more or less widespread emergence of the sea bottom. Each began with a subsidence which gradually extended to a maximum at the time when the great limestone was formed. The parallelisms are not exact, but they are certainly suggestive. End of section 25.